I am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science, Jesus and Mary College, University of Delhi. So friends, we are talking about data mining in this series of lectures, and in the last lecture of this series, we were talking about dimensionality reduction for pre-processing of data to suit the data mining algorithms. And we had seen that different approaches can be used for data mining, for dimensionality reduction in data mining, such as we were talking about feature selection, we had talked about feature weighting, and we were talking about feature extraction, feature creation rather. So feature creation, we had seen that feature creation basically means that we are going to create new features from the existing features which are present, and the new features that we will be creating will have lesser number and it will be more concise than the previous subset of feature or the previous set of features, right. So we had looked at the aspect of feature creation in this, and we had also seen that feature creation has got limited applicability and it is more commonly used in case of image processing. The next approach to feature creation can be mapping the data to a new space, right. That is, we are creating a totally different view of the data and which will reveal important and interesting features. Okay. So, for example, let us look at the time series data. Okay. Now, time series data, we all know that it contains periodic patterns, it has got some periodic patterns. Now, if we have a data set which has got a single periodic pattern and not much noise, okay, then the pattern can be very easily detected from the time series data. But if we have a data set which has got number of patterns and also significant amount of noise, now these patterns will become very hard to detect. So what is the solution to this? In this case, we will try to map this data and we will try to find these patterns which are hidden in this. We will try to detect these patterns by applying Fourier transform to the time series in order to change to a representation in which frequency information is explicit. So with the frequency information that we are going to get using the Fourier transform, we will produce a new data set and the attributes will be related to the frequency. Why? Because earlier the pattern was hidden. Now when we are using the Fourier transform to the time series data, then the patterns will emerge, because another, you will have another feature which is added, that is the frequency. So earlier we did not have this feature in the data set, but now we have created it using the Fourier transform to the time series data, right. So now this new data object is created and the attribute will be related to the frequency. So likewise, we can have multiple approaches by which, we can try to reduce the features. Now another very important set of techniques which are used is discretization and binarization, right. These are two terms which go simultaneously hand in hand in data mining algorithm, right. For example, we know that some data mining algorithms, they especially the classification algorithm, they will require the data to be in the form of categorical attribute, right, because they have to divide the data into specific categories, right. And there are other algorithms which will find association patterns which require that the data has to be in binary attributes. If you want to find out association between two attributes, then the attributes have to be binary. So what is done? It is important that we transform the continuous attribute into categorical attribute, and this is known as discretization. That is, you are making a continuous attribute into a discrete attribute. You are breaking it into different classes, different categories, okay. And both continuous and discrete attributes, they may need to be transformed into one or more binary attributes. So binary attributes means that the attribute will have value as 0 or 1. So this process of converting the discrete attribute or continuous attribute into binary attribute is known as binarization. Okay. So two processes are being talked about here. One is conversion of continuous attribute into discrete attributes, that is known as discretization, and both continuous and discrete attributes will be transformed into binary attributes called binarization. Okay. Now for example, if there is a categorical attribute, okay, and it has got a large number of categories or large number of values, okay, and some values which occur very infrequently, then it can be beneficial for a data mining task to reduce the number of categories by combining some of these values, right. For example, if we have a rating attribute, we have a feature in which rating is to be done, categorical rating is to be done, and we see that we have two categories, say poor and very poor, in which the data is occurring very less number of time. Both poor and very poor have got very less number of instances, right. So what can be done? These two categories of poor and very poor could be combined into one category, right. So therefore we will have lesser number of category, right. So the best approach to discretization or binarization is the one which will produce the best result for the data mining algorithm that we are going to use for analyzing the data, right. So what approach to use, how the categories are to be made, or how the data is to be converted into binary attribute will depend upon the algorithm which is being used, right. So basically it is not practical to apply a criteria directly, right. So discretization or binarization is performed in a way that satisfy a criteria that is thought to have a relationship to good performance for the data mining task being considered. So we will not look just at the approach or just at the criteria, but we will look at the criteria along with the algorithm in which the data has to be used. Only then the best results can be obtained. So the best discretization depends on the algorithm being used as well as the other attributes which are being considered, right. So discretization of each attribute is considered in isolation, okay. So we cannot consider that if you are converting one continuous attribute into categories and there is another continuous attribute also which is you want to convert into categories. So both these have to be done in isolation with each other. There cannot be a correlation between the two attributes which are being discretized. Okay. So let us look at binarization first, that is how we will binarize a categorical attribute. Okay. So if you have a categorical attribute which has got m values, okay, then what you do is you uniquely assign each original value to an integer in the interval of 0 to m minus 1, okay. And if the attributes are ordinal, right, that is ordinal means that the order is also important because they can be arranged in a particular order, then the order also has to be maintained by the assignment, okay. Next what we will do, we will convert each of these m integers into a binary number, right. So what we have done, we have got a categories. For each category we are assigning an integer, okay. So starting from 0 we assign an integer and then we convert those integers into binary numbers, okay. So if we have got, say if we have got binary m number of attributes, so you will require log of m with the base 2 binary digits to represent those numbers, okay, if you have n binary attribute, right. So if we are looking, let's look at an example and understand this thing. So we have a categorical variable which has got 5 values, say awful, poor, okay, good and great, right. Now it would require 3 binary variables, that is x1, x2 and x3. So if we look at this table, it is very clear. We have got categorical variables, which are 5 categorical variables. So we will assign each of these variable an integer value, say from 0 to 4, because there are 5. So 0 to m minus 1, that is 4 values, and for each integer value we are going to convert it into an equivalent binary attribute, converting it into binary attributes, right. Now this type of transformation which we are doing, it can cause complication, right, because what you see is that there is unintended relationship which is showing in the transformed attribute. Like for example, here the categorical value good, right, in this the attribute x2 and x3, they are showing a correlation amongst themselves, which actually does not exist, but it is being shown here because of this transformation strategy that we are using here, right. So this can cause a problem because of the correlation, unintended relationship which are being shown in this kind of table that is created, right. Furthermore, association analysis will also require asymmetric binary attributes where only the presence of the attribute, that is value 1, is important, right. So we had seen that in asymmetric attributes we are only concerned about the places, the data where the value is 1, right. So it is very important here to introduce one asymmetric binary attribute for each of the categorical values. So instead of having 3 binary attribute, we will now have 5 binary attribute. Why? The fifth, because for association problem we have to introduce this asymmetric binary attribute wherever there will be asymmetric attribute. Likewise, for association problems also, it will be necessary to replace the single binary attribute with 2 asymmetric binary attributes. So every binary attribute will be replaced by 2 asymmetric binary attribute, and we will have 1 binary attribute for the asymmetric. So in all there will be 5 binary attribute, right. So for example, if we consider a binary attribute which records a person's gender, that is male or female, right. Now for traditional association rule algorithm, that is which has got 3 binary values, this information will be transformed using 2 asymmetric binary attribute, that is one that is a 1 when the person is male and one that is a 1 when the person is a female, right. So 2 binary values are there, m and f. So m is 1 when the person is male, f is 1 when the person is female, okay. So this can be used, but the better strategy in this case also, what will happen, there will be a correlation which will be established in certain cases, because so therefore what we will need is, we will need 2 more binary values, which binary attributes to be inserted for the asymmetric attribute. Now if we look at discretization of continuous attributes, that is how you are going to break the continuous attribute into classes, okay, or into categories. So discretization is typically applied to attributes that will be used in classification and analysis, association analysis. Association analysis means where we are trying to find out the relationship of one attribute with the other, and classification means that we are dividing the entire data into classes or categories. So transformation of a continuous attribute into a categorical attribute will involve 2 subtasks. Now what are the 2 tasks? That we have to decide how many categories have to be created and how to map the value of the continuous attribute to these categories, right. So we have got a set of continuous attributes, okay, and now these continuous attributes have to be divided into categories. Say we want to create number of categories, say n categories, and then what all values will fall into that category n. So basically this involves 2 tasks or 2 steps, The first step will mean that the values of the continuous attributes are sorted, okay, and they will be divided into n intervals by specifying n minus 1 split points, right. So we'll divide it into categories, say 0 to 5, 6 to 10, 11 to 15, like this we will divide it, and we will create those split points. And after you have created those split points or those categories, then we will assign the values in that each interval. So we are going to do a mapping, basically, that all the values in one interval will be mapped to the same categorical value, okay. So therefore, what the problem of discretization is that of deciding how many split points to choose and where to place them. So you have a data from minus infinity to plus infinity. Now how do you choose that, how do you divide this data into equal split points? Now you can do it using various approaches, but the important main focus of this approach will be to choose the number of split points and to place those split points. So the result can be represented either as a set of intervals like x0 to x1, x1 to x2, like this, okay. And so this can be minus infinity to plus infinity, or we can have as a series of inequalities, that is x0 is less than x is less than equal to x1, like this. So we can have it either way, you can create the intervals or you can create the series of inequalities, okay. Now in this case, in discretization, when you want to you want to find out the number of split points, you can have it in two ways. You can have unsupervised discretization or you can have supervised discretization. So what is the basic distinction between discretization method for classification is that whether the class information is used, which makes it supervised, or whether the class information is not used, which makes it unsupervised. So if the class information is not used, then relatively simple approach will be used, which will be common, okay. Say for instance, the equal width approach will divide the range of attributes into a user specified number of intervals, each having the same width. Like what we are saying is that we divide the values as 0 to 5, 6 to 10, 11 to 15, like this. So the user will specify the number of intervals and we will divide the data. Now in this case, what will be the problem? The problem will be of the outliers, because they may not fall into the final intervals, because an equal frequency or equal depth approach will be more suitable, which will try to put the same number of objects into each interval. So this is more preferred, because in this the problem of outliers will be taken care of. So instead of dividing the data in user specified number of intervals, we actually divide it into equal depth, that is what is the frequency, according to that we are going to create the classes, okay. Then the next thing that we look at for dimensionality reduction is variable transformation. Now variable transformation means that we are transforming the value of a variable. We are applying some transformation to the value of the variable. So for each object the transformation will be applied to the value of the variable for that particular object. Now transformation to the value means that it can be a statistical transformation, it can be a mathematical transformation, that is we apply some statistical function, we apply some mathematical function to the value of the variable and we try to transform the value, right. So variable transformation is if it is only the magnitude of the variable which is important, then as I just said, the value of the variable can be transformed by taking the absolute value, right. So we can have two types of variable transformation. The first is simple functional transformation and the second is normalization. Normalization, or we also say as standardization, right. So simple functional transformations are basically these are simple mathematical functions, as I just explained, which are applied to the values of the variable. So if we have a variable x, then example of a simple functional transformation could be, finding out x to the power k, or log of x, or e to the power x, or square root of x, or 1 upon x, sin x, etc., or modulus of x. So if it is, a simple function can be applied to the value of the variable will transform, right. So these square root or log or 1 upon x, they are generally used to transform data which does not have a Gaussian or normal distribution, okay, into the data which will have a normal distribution, because we had seen that data can have multiple types of distribution. So if you get a data which does not have a normal distribution, then you apply these simple functions to it so that it follows the normal distribution. Like for example, if we are looking at a variable, and the variable is the number of data bytes in a session, okay. Now the number of data bytes in a session can vary from 1 to 1 billion. So therefore this is a huge range, and it will be very advantageous to compress it by using a log 10 transformation, right, because it is, it's a huge range, so we need to find out the transformation of it. Now in this case, the sessions that transferred 10 to the power 8 and 10 to the power 9 bytes will be more similar to each other than the sessions that transferred 100 and 1000 bytes. Why? Because 9 minus 8 is 1, whereas 3 minus 1 is 2. So the difference or the gap between the first instance or in the first session is lesser, and in the second session it is more, right. Like in other applications also, like for example network intrusion detection, this may be what is desired, since the first two sessions most likely represent transfer of large files, 10 to the power 8 and 10 to the power 9 bytes means larger files, but the latter two sessions where you are transferring 10 bytes and 1000 bytes, it could be two quite distinct types of sessions. So what we are looking at is, we are trying to look at anomaly detection in network fraud, right, in network intrusion. So in that case, applying this kind of function can give you, finding out a simple log of the value can give you a lot of information, a lot of data. So variable transformations should be applied with a caution, definitely, because they can change the nature of data. Now how they can do that? If the nature of the transformation is not fully appreciated, like for example the transformation that we are applying is 1 upon x, which will reduce the magnitude of values that are 1 or larger, because you are dividing it by x, but it will increase the magnitude of the values which are less than 1, that is between 0 and 1. How we are saying it? Say for example the values are 1, 2 and 3. So the values will become 1, 1 upon 2 and 1 upon 3. But if the values are 1, 1 upon 2 and 1 upon 3, now in this case the values will become 1, 2 and 3, because you are going to divide 1 upon 2 by 2, so it will give you the value 2. So therefore it is important that it is clearly understood, because here the nature of the value is changing when you are applying the transformation, right. So for all sets of values, the transformation 1 upon x reverses the order, right. So the effect of the transformation is very, very important, and to understand the effect of transformation, that is what kind of transformation effect the transformation is going to bring on the data set, it is important to answer a few questions. What are the questions? That what is the desired property of the transformed attribute? Why are we doing the transformation? Does the order need to be maintained? Do we need to keep the order? Is it an ordinal attribute, right? Does the transformation apply to all values, especially the negative values in 0? And what is the effect of the transformation on values between 0 and 1? That is, the values which are less than 1, what is the effect. So, we have to apply the transformation to all the values and first ascertain what is going to be the effect on the final data, otherwise this is going to be problematic. Then the second type of procedure which can be done for the standardization procedure, or for the process of ascertaining the value, it can be normalization or standardization. So, the goal of standardization or normalization is to make the entire set of values have a particular property, right. Like for example, in statistics we use standardizing a variable, right, we commonly use it. Now, if we have a value which is the mean value of the attribute, okay, and S is the standard deviation, right, then the transformation equation can be found out using this. So, in variable transformation, what we are doing here, we are actually finding out one value for the entire, one common value for the entire set. So, this value is going to create a new variable that has the mean of 0 and standard deviation of 1 by applying this kind of normalization procedure or by using simple values like mean and standard deviation. So, if the different variables are to be used together, like for clustering, then such a transformation is necessary to avoid having a variable with large values dominate the result of analysis, because we are trying to standardize. If some variable has got extremely high value, other has got extremely low value, so we are trying to bring them at par by taking the average or mean and then also using the standard deviation function in this case. Right. So, therefore, this entire process of finding out the values of the variable, of feature creation or feature selection, all these are ultimately going to lead to the factor of dimensionality reduction. To the ultimate goal of the exercise is dimensionality reduction. Whatever approach we use, the main goal is to make the data best suited for your data mining analysis algorithm, whatever you are using, whether it is clustering or association analysis, whichever analysis you are using, this is going to help. So, with this we give a halt to today's lecture. We will continue with another interesting topic on data mining in the next lecture. Till then, thanks.